In this section, we're going to take a look at the different types of skeletal muscle fibers. There's basically three different types that we'll be looking at: type 1, type 2A, and type 2B, or type 2X. We'll look at what causes muscles to fatigue, and then how we adapt to both endurance training and to strength training, where we get hypertrophy or where we get atrophy from disuse. And we'll finish up by looking at how muscles change with age. So your book talks about two different types of muscles. In general, in the community, we'll look at fast twitch versus slow twitch type muscles. The fast twitch are also called fast glycolytic, or slow twitch will be slow oxidative. The fast glycolytic we think of as being our anaerobic pathways. This is for our strength or explosive energy training. When we look at the fibers, we're going to see that these are going to be the lighter ones that are in color. They're whiter because they have less myoglobin in them. And the myoglobin is what's going to end up causing these muscles to stain dark. They're also going to have fewer mitochondria in them. And as a result, they're going to fatigue quickly. The slow twitch, on the other hand, are going to be just about the opposite. They're going to be slow oxidative, so they're going to be using the aerobic pathways. Their motor units are going to be much smaller. So remember, motor unit is that alpha motor neuron and all the muscle fibers it innervates. It's going to have smaller motor units. And if you think about it, that makes sense because the fast ones are where your strength and explosive energy, they're going to have the high, big motor units in them. The slow twitch also are going to be darker in color. That's because they're going to have more hemoglobin and myoglobin. Hemoglobin surrounding, a lot more myoglobin inside the red fibers, inside the fibers that are making them red. And this is going to promote our endurance. So in all actuality, there's really three different types of muscle fibers. Those fast twitch muscle fibers can be broken down into type 2A and type 2B, or type 2X. Type 2X is really the more recent nomenclature for that. So the fast glycolytic, the FG, are going to be our fastest, strongest types of fibers. These type 2As are a combination, really, of type 1 and type 2B. So we call them fast oxidative glycolytic, or FOG, and they kind of move like fog. They're going to be a little bit more endurance, but they have a little bit more power to them as well. So you can see they have a few more of these red fibers in them. You see a lot of red fibers over here in the type 1 muscle fibers. And the type 2s are going to be just a combination. So they're going to, instead of being white or red, they're going to be more pink in color. Now I made this little chart here, and I can't click through it, so I'm going to write through it with you, but I want you to think about the differences in these fiber types as we go through them. So if we look at just the size of the muscle fibers, these type 1s are going to be small compared to the type 2Bs, which are going to be really big. They're going to be super large. So I'm going to do a couple like this. And the type 2As, somewhere in between, we still call them large, but maybe I'll just give them one arrow up and down, or up. I made this so that when you are going through the PowerPoint on your own, you can click on these boxes and reveal the same things, but this way you can kind of test yourself as you go. Twitch speed, so how fast are they? Well, these are going to be slow. Type 2s are going to be really fast. And the type 1s are going to be, maybe we'll just give them one or two arrows going up. Those are semi-fast. Aerobic capacity, type 2s are going to be really strongly aerobic. Type 2Bs, not so much. Type 2As, somewhere in the middle. Myoglobin, mitochondrion, a lot in these type 1s, just a little bit in this type 2Bs, and somewhere in between in those. Force, not so much. Little force there, a lot of force here, and somewhere in the middle. We can do it like that. So you kind of get the picture of all these. Fatigue resistance. These guys are going to be highly resistant to fatigue, so they don't fatigue very easily. These guys, not very fatigue resistant. So one arrow up, or if you want to think of it as one arrow down, they fatigue really easily. Color, we're going to have red for the type 1s, we're going to have white for the type 2s, and we're going to be pink for the type 2As. And I'll kind of do this. energy system, we're going to have aerobic here. Here we're going to have anaerobic. And this is going to be a combination of the two, so we'll call it more aerobic. But it can do aerobic and non-aerobic. This is a chart in your book that kind of goes through the same thing. I like my chart a little bit better because you can see the three different types and just clearly just up arrow a lot or a little. One thing I want to point out here is that under respiration, they have aerobic for all three categories. And really this third category, this fast glycolytic, it's going to be more anaerobic respiration. So we can look at how quickly these things fire. So this is time in milliseconds, and this is how much tension they produce. So this is looking at their kind of maximal tension. And you can see these type 2X fibers or type B fibers, this graph categorizes them as this first one for A. So this is your type 2B, type 2X. So you can see these fire off really quickly and they get to their peak tension very fast. The fast oxidative glycolytic, the ones in the middle, are going to take a little bit longer to reach their peak tension. And then the slow oxidative, the type 1s, are going to take a lot longer to get to their peak tension. And this is just relative peak tension to themselves. I think these type 2Bs are going to actually go up quite a bit higher, but this slide is more talking to you about how quickly they can reach to their peak tension. So the type 2Xs or type 2Bs get there much faster. We can kind of look at how much of these fibers we have in our skeletal muscles. And most every muscle is going to have a mix of these type 1, type 2A, and type 2B fibers in them. And what's kind of interesting is if you kind of we'll pick a couple of them here. World-class sprinters, well, you'd expect that they were going to have a lower amount of the slow type 1 fibers and a much higher amount of these fast twitch fibers relative to somebody who's a world-class marathon runner or an endurance athlete, where they're going to have a lot of type 1 fibers compared to type 2 fibers. And you can just kind of see how this changes throughout. What I thought was kind of interesting is that a person with a spinal cord injury, you can see that they really are depending primarily on the fast twitch type fibers. As that muscle atrophies, you're going to lose some of those slow type 1 fibers. And it's the fast twitch, the anaerobic part, that's going to be what survives in people with spinal cord injury specifically. So why do our muscles get fatigued? By fatigue, we're saying it's the reduction in the ability to generate force in a muscle. Well, there's several reasons why we believe the muscles fatigue. The first one is going to be due to the accumulation of extracellular potassium. Remember that potassium is mostly in the muscle cell, within the cell. And when that action potential comes along, we're going to have sodium come flooding in, but then the repolarization process is all that potassium going out to get our cell back to resting membrane potential. Well, the problem is if you keep stimulating that cell over and over and over, you're going to end up putting a lot of potassium out of the cell. And that's going to cause the cell to become more negative and make it harder to fire again and depolarize. So that's one reason that the potassium is going to interfere if we have too much potassium outside compared to inside. And we get it outside because we're doing all this depolarization. The other thing is that because that potassium is going out so much, some of that potassium apparently can get into the T-tubule and muck up the voltage-gated calcium channel and calcium release channels, making it more difficult for the calcium to leave that sarcoplasmic reticulum. So it can cause fatigue that way as well. We can also have a depletion of our stored glycogen. And when you don't have enough glycogen, that can actually have an effect on decreasing the amount of calcium that's released from that sarcoplasmic reticulum sitting in here as well. There's some thought that lactic acid accumulation would cause muscles to fatigue, because as you increase the lactic acid, you're going to lower the pH. And we all learned in one of the very first labs that we had is that if something becomes too acidic, it can actually start to denature some of those proteins. a few more here. If we increase our concentration of phosphates, and that can happen due to phosphocreatine breakdown. And we believe that that's going to cause, if there's not enough phosphocreatine and it's releasing all these phosphates, it can reduce the amount of force that muscle can provide with its contraction. Clearly, you might think, well, if you don't have enough ATP, then that muscle is not going to generate energy. And that's true. But one of the main reasons, and we see this mostly in the type 2B fibers or type 2X fibers, is that if you don't have enough ATP, you're not going to be able to pump that calcium back into the sarcoplasmic reticulum. And this is really important for those fast twitch muscles because they got to regenerate that calcium over and over and over again. They got to flood it out to the troponin, but then they quickly got to get it back in so they can use it again. And that's where a lot of the ATP is being used that's going to influence muscle fatigue. And likely, if you have a buildup of ADP, that's thought to decrease the velocity of the muscle shortening. So the muscle's not going to be able to shorten as quickly. All of these are going to result in muscle fatigue. The last one is called central fatigue. This is different than everything we've been talking about so far. So far, everything we've been talking about is what we call peripheral fatigue, meaning outside of the central nervous system, it has something to do with the muscle itself. But in central fatigue, it's actually fatigue of that upper motor neuron in the central nervous system, with the ultimate result of producing less acetylcholine at that synaptic junction, at that motor end plate. So we can see it here. If we put this together as one big slide, we have our central nervous system, and if this upper motor neuron is getting fatigued from firing too much and it doesn't stimulate our alpha motor neuron, then when this alpha motor neuron comes out into the peripheral system, it may be not firing and not releasing its acetylcholine, or you could not have enough acetylcholine that's left in this alpha motor neuron to stimulate the motor end plate of this muscle fiber. And then we've got all the other problems of too much potassium in this T-tubule, of not enough glycogen storage, of not enough ATP or ADP, and then our central fatigue. So how does our body respond to endurance training? Well, first thing is it's going to be able to use our fatty acids much better. And it's going to be able to store triglycerides in the muscle cell much better. So we're going to increase our storage of those great 108 producing ATPs per 16 fatty acid chain. We're going to be able to store them and use them more effectively. Because remember, it takes a while to get into that acetyl-CoA form so it can go through the Krebs cycle. We're going to increase our lactate threshold. So remember that shift in the lactate threshold curve where it was shifting over to the right, where you're not building up lactate as quickly as you would if you're not trained because you've got more mitochondria. You can decrease the type 2BX and increase type 2A muscle fibers. So this is kind of interesting. So we can actually change some of these muscle fibers with training. And there's kind of a saying that goes, you're born a sprinter, but you can be made a marathoner. And what that means is that we can take some of those 2B fibers and we can actually change them into 2A fibers. But unfortunately, it doesn't go the other way. With powerlifting, you're not going to make a type 1 muscle fiber into a type 2 muscle fiber. You can only go from type 2B to type 2A muscle fibers. Kind of like think about red and white clothes in the wash. If you take a pair of white socks and throw it into a load with some red clothes in it, you're training that sock to be red. You can make it kind of pink, which is what we see. But if you take a red pair of shorts or a red pair of socks and throw it in a whitewash, you're not going to make that red sock white. It's going to stay red. So that's kind of how you can think about training, affecting, and changing those muscle fibers. You go from 2B to 2A with training, but you can't go the other way. We can actually decrease our insulin sensitivity. So remember, if you have too much insulin going out, that can cause downregulation in the cells for the receptors. Well, if you're using all that sugar and burning it up right away, that's going to be okay. So you can keep that keep throwing out that insulin, keep burning those carbs because you know that you're going to use them. And the last thing here is it's going to increase the number of mitochondria with training. And that's what we're going to see with increasing our lactate threshold, because if we have more mitochondria, then we're going to be able to use more oxygen effectively. So we won't need to make that lactate as quickly, and we'll be able to do more work without reaching that threshold so early. So these are 5 different ways that we can adapt with endurance training. Your book lists a whole bunch of ways. If you use my 5 ways, that's going to be good enough for our purposes. But I mean, if you read through these, they kind of make sense with what I've just been talking about. Okay, so if we change gears from endurance to strength training is a little bit different. What you do with all that powerlifting and strength training is you're actually causing the muscle cells to hypertrophy. And remember, with hypertrophy, we're not making more cells, we're just making them bigger. So these type 2 muscle fibers get thicker because we're making more actin and myosin. So we're making a lot more sarcomeres. And what can happen is that, remember, those sarcomeres are all lined up in those myofibrils, and you can have a lot of myofibrils within the muscle fiber, the cell. So with all this training, those myofibrils can actually split sometimes into 2 myofibrils, and then you're going to increase the size. So if this is a cell down here, you can see that this cell actually can increase in size a couple of different ways. One is the sarcoplasm, so the fluid inside the cell can increase, and you can see it increase in the cell size here. But then you can also split these myofibrils and get more myofibrils, and that eventually is going to make that cell bigger. When you do that, just to be aware, it's not just actin and myosin, but you need all those structural proteins that hold them together. You need that titin that's holding the myosin to the Z disc. You need the nebulin, which is holding the G actin, all those little pearls of G actin together into the F actin, that big long chain. The nebulin is doing that. And then this other protein I don't think I've mentioned before, obscurin, it's just kind of wrapping around the M line and the Z disc, kind of holding that whole sarcomere all together. So you need all these guys along with the actin and myosin to make the muscle cell bigger. So this is just kind of a visual of the same thing. We're hypertrophying. This was a picture of me in my 20s. Ha! I don't think so. This is that muscle belly. We've got the muscle fiber, remember, and then within the muscle fiber, we've got these myofibrils. So this myofibril, which is made up of the actin and the myosin filaments, this guy is what's splitting within the cell, making more of these myofibrils, making the cell bigger and bigger. The opposite of hypertrophy is called atrophy, and atrophy is just a reduction in the muscle size, and we get that in 2 different ways. One is a neurogenic atrophy, and that's when you have some type of disease like amyotrophic lateral sclerosis, or a trauma where that nerve isn't able to signal the muscle to fire anymore, and that muscle, it's going to do the old use it or lose it thing, where if that muscle isn't firing, it's not going to be making all those proteins and regenerating itself. And same thing here's disuse atrophy. Basically, if you're laid up in bed, let's say that you're sick for a while, or if you're injured and you have put yourself in a cast and you can't move that leg, so you're not moving the muscles, you can actually get a quite significant reduction in muscle size. This right side of his calf is what he would normally look like, and the left side is due to disuse. As we age, there's a normal typical decline in our muscle mass. This is usually pertaining to our type 2 muscle fibers. So those fibers are the power and strength fibers. And unfortunately, this is what you need to get up out of a chair or get up off the floor. But the good part is that we can actually train our geriatric population with weights and regain a lot of that muscle mass that they naturally lose. You're also going to see a reduction in the capillary blood supply. This can be because maybe the capillaries are getting clogged and not being effective, or if they're not being used, they're not going to be growing as much. So this can be helped again with more endurance training. We also have something called satellite cells in our body. And satellite cells are basically like stem cells. And those stem cells are used to repair the myofibrils, or can actually replace some of them when they get damaged too much. So if we have fewer stem cells, fewer satellite cells, we're not going to be able to replace those cells that we're losing as easily. Often this can lead to a condition called sarcopenia, which is basically just a loss of muscle mass. And from the time that you're 20 years old until you're about 80 years old, the average person is going to lose about 45% of their total muscle mass. A lot of this we think is influenced by the mitochondria. And as the mitochondria die, the body actually has a harder time with autophagy, with the ability to clean up the mess of those old mitochondria. So it's not cleaning them out as well, and it's not replacing them as well. So you're getting more garbage laying around, and you can't make new mitochondria easily, so you're not going to be as efficient and effective at creating ATP for those muscles to use. And the last thing on here is we have an increase in something called myostatin production. And myostatin actually inhibits the satellite cells, and it, as a result, prevents muscle growth. We've seen in studies with mice where they take out the gene that produces myostatin, and they get this big, bulking, strapping, strong mice that so the muscle's allowed to grow. But in humans, we see this increase in myostatin, unfortunately, with age, and that's going to suppress our muscles' ability to grow. So that ends this section, and we'll look now at some of the sensory organs that are going to be involved in the muscle in our next video.